Welcome back for this last lectures on experiments on ultra-cold fermions. As I announced yesterday, today I would like to discuss what happens when you try to excite your cloud and to see the response of a strongly correlated cloud of fermions to some external excitation. And so the first experiment I would like to discuss is a very simple one, which is that before we were dealing with an atom which are in their trap, nicely sitting at rest at thermal equilibrium, and now all of a sudden you compress them in one or all directions. So it means that you switch one of the trapping frequencies from one value to the other. And so obviously what is going to happen is that the cloud will oscillate, and you can try to measure the oscillation frequency versus the scattering length, so depending on where you are in the BEC to BCS crossover. And so the most precise measurement according to this scheme was performed by the group of Rudy Grimm in Innsbruck. And so this is what he observed. Essentially, so he had a very elongated cloud, and so he could excite the so-called breathing mode, so the oscillation of the radius of the cloud, either along the weak axis, so this is omega z here, or along the tight axis, omega x or omega y. It's a cylindrical. And so this is what they measure. So the frequency seems to depend on the 1/kFA. And so what I would like to discuss today is how we can interpret this data, and in particular how these curves here, which correspond to the prediction of the BCS theory here in black and some more advanced Monte Carlo simulation there in red, are obtained. So you used how from some equation of state of a system at equilibrium in a homogeneous system, in a homogeneous trap, you can deduce some prediction for these oscillation frequencies. So I'm going to switch to the blackboard for this. Yes. So our main problem here, our main challenge here is, as usual, that we is that it's very difficult to find some reliable theory that we can use to describe these systems. So for instance, you could try to describe the dynamics of the system using BCS theory, but as I said in the previous lecture, BCS theory is very nice quantitatively when you are on the BCS side of the Feshbach resonance, and if you want to be quantitative across the BC to BCS crossover, unfortunately it's not accurate enough. So you need something which is more robust by BCS theory. And so we're gonna think along the line of local density approximation and try to find a way to describe these experiments using as few hypotheses as possible. And the equivalent of local density approximation for dynamical systems or for dynamical phenomena is hydrodynamics. And so I would like to show you that using some very simple assumptions, we can show that our system, our gas, will obey some hydrodynamical equations, which are some, as I said, some generalization of the local density approximation. So today we're going to talk during most of the lecture about hydrodynamics. And so the idea of hydrodynamics or local density approximation is to say that locally you can define some intensive thermodynamical quantities. So for instance, density, so for instance, temperature, pressure, and some quantities which are more related to dynamics, velocity. So we can locally define pressure that depends on R and T, density that depends on R and T, a chemical potential that depends on R and T, a velocity that depends on R and T, etc. All these are well defined locally. And so they're going to satisfy some local equilibrium approximations. And so what we're going to do is to write some conservation equation for these quantities. So the first conservation equation that we can think of is the conservation of the particle number of the mass. So if I call rho the mass density, so it's m times the particle density, it satisfies a conservation equation which is simply d rho over dt plus the divergence of some flux of matter, which is equal to 0, And you know here that the flux of matter is just the density times the velocity. So this is the first equation we want to write. The second equation we're going to write is the conservation of momentum. So the conservation of momentum will tell you that if I look at momentum along the direction I, let's say, so I have something which is d rho vi divided by dt. So m times v is the momentum, and so the density of momentum will be the density of particles times mv. There will be some current of momentum that I'm going to write this way. I'm going to explain to you what it means, this current of momentum, but this is essentially some local transfer of momentum between different regions of the fluid. And obviously, the momentum is not strictly conserved in the sense that if you take a system, it can exchange momentum with the with the outer world, and this transfer of momentum is described by some external forces. So there is some density of force that transfer momentum from the outside to your cloud. For instance, if you have a trapping potential, the trapping potential will convey some momentum to the cloud. So what is this Pij? So this Pij tells you essentially that if you consider for instance momentum along x, and that your momentum along x varies along the direction j, you can have some transfer of momentum. So what does it describe? So let's try to imagine what is Pxy. Pxy is the following. So if you have, for instance, a gradient of velocity, so I plot here the velocity along y, and so this is a coordinate x of the velocity. So I have a shear velocity along x in this direction. So the velocity along x vary along y, and so I will have a transfer of momentum along x because this velocity will tend to equilibrate. So you see, I can create a flux of momentum in the direction y because the particles which are here will transfer momentum to there to equilibrate the momenta along x. So this is the meaning of these components here, of this flux of momentum. So we know what is the density of momentum. We know obviously what are the external forces. So in our case, it's going to be simply the density of particles times the derivative of the trapping potential. And so now the game is to try to find what is the expression of this flux of momentum. So what is the expression of Pij? So I'm going to start in a very simple situation, and then I will try to complexify it more and more to get some general expression for Pij. So the simplest situation I can imagine is a fluid which is at rest. In this case, there is no velocity, and so this Pij, this current, depends only on the other local quantity, which are the pressure, the density, the chemical potential, everything. So when I'm at rest, obviously, I don't have any dependence on velocity. And if I'm at rest, I don't have any preferred direction, because obviously my fluid is isotropic. So it means that Pij should be some constant times delta ij by isotropy of the system. And now we would like to understand what is this A. So this A again will depend on the local properties, of the local thermodynamical properties of our cloud. So if I insert this expression for Pij in the in my conservation momentum equation, what I see that the derivative with respect to j of A delta ij is equal to the density of force, or if you prefer, dIA is equal to Fi. So at equilibrium, my cloud should satisfy this equation here. So can you guess from this expression what is A in this case? Nope. The potential does not depend on the properties of the cloud. It's something which comes from the outside. So I would like a property which depends on the cloud itself. So at equilibrium, a fluid satisfies the static equation Fi minus dip is equal to 0. The force minus the gradient of the pressure is equal to 0. So I see that at equilibrium, Fi is equal to dip. And so that allows me to identify A to P. So A is nothing but the pressure of the fluid. So at rest, Pij is just this, the pressure times delta Ij. So now I'm going to set the fluid into motion. We're going to first assume that it's a uniform motion. And to get the expression of Pij in this case, what we're going to use is now the Galilean invariance, the fact that our equation should also be valid, in any Galilean frame. So I wrote them in some frame, my lab frame, but a priori they should be valid in any frame. And so here I work in a frame where positions are defined by xi times by t. And so I'm going to work in a new frame which moves at a velocity u with respect to the lab frame. And so I define a new position x prime I, which is equal to xi minus uit. And the t prime will obviously be the same, because I'm not considering Einstein relativity here. It's just standard Galilean relativity. And obviously, in the new frame, the velocity field will be modified, because the velocity in the new frame will be simply v prime I is equal to vi minus ui. And so now I would like to write the equation of motion in the new frame. So I'm just going to forget about this term, because obviously, again, that will not depend on the frame where I'm working. The force, external force, do not depend on the frame Galilean frame where I work. Sorry, and so I'm just going to focus on these two terms here. So I need to re-express the derivative with respect to time and with respect to position in the new frame. So using the usual chain rule. So I said that the derivative with respect to time is just dt prime divided by dt times dt prime plus dx prime j divided by dt times dx prime j. So this will be dt prime minus uj d prime j. I forget to mention, but it's obvious, I'm using the Einstein conventions where I sum over the repeated indices. If I look at the derivative with respect to position, let's see, it's going to be dt prime divided by dxi dt prime plus dx prime j divided by dxi d prime j. So this is just 0, because I don't have any dependence of t prime with the position. And dx prime j is just delta ij. And so this will be d prime I. So the take-home message here is that the space derivative are not modified when I change the frame, but the time derivative is. So now if I take my conservation of momentum equation, or at least the left-hand side term, I must write that. So dt prime minus uj d prime j that acts on rho times vi, so it's going to be vi v prime I plus ui plus d prime j pij is equal to, again, phi, but again, this doesn't matter very much here. Which one? First line. Which one? This one? Okay, which equation are we talking about? Because yeah, so when I write this, dt is actually d over dt. This is what you meant? Or is it something else? Okay, you're doing wrong. Okay, so back to business. So I have this dt prime or rho v prime vi prime, which is here, which is the usual term, plus some term which is, so the next term which will be ui times the derivative with respect to time of rho v prime I minus, so uj d prime j of rho v prime I plus rho ui plus d prime j pi ij equal fi. And so the goal here, you see, is to write all these terms as some flux, so some divergence. So I already have parts of it here, because this is already some divergence terms, so I can add them to Pij. And so here, what I need to do is to replace that term by something which is divergent. And so this is what's it again?
The second term you're writing.
Oh yes, sorry. You're right. Because actually I was gonna use the conservation of mass, where indeed there is no such thing. So using the conservation of mass, you can replace the derivative with respect to time of rho by a gradient. So which could have just be minus dj of rho v prime j, because here I'm working in the new frame. And so you see that all the terms which are not this one are in the form of a divergence. And so actually I can gather all these terms under this form. So I get t prime of rho v prime a I plus a divergence, so in the new frame, of Pij. And so you can write this the following way. So if you gather everything and you re-express ui in function of all the new velocities on the two frames, plus rho v prime I v prime j minus rho vi vj is equal to fi. And so this is gonna be my new momentum current in the new frame. Okay. So pi prime j is equal to Pij plus rho v prime I v prime j minus rho vi vj. So now it's very easy to find the expression of the current for a fluid at a given velocity, because if the fluid moves at a uniform velocity, so the velocity field is uniform, is the same everywhere, I can define a Galilean frame where the fluid is at rest. So now I'm going to work in a frame, where the fluid is at rest. So in that fluid, V prime I is equal to 0 by definition, and P prime ij is given by the expression of the flux of the current and momentum in the rest frame. So this is this expression here. And so using this expression there, what I deduce is that Pij is equal to P delta ij plus rho Vi Vj. I just replaced here, I took a shortcut, I replaced U by V prime minus V. Okay, in some sense, this is quite easy to understand, this expression, because so you're looking at the momentum, the flux of momentum along I, so the density of momentum along I is rho times Vi, so this is this. And you're looking at a current along the direction J. So what it means that when you have a particle that moves at a velocity, let's say V along x, so rho Vx, since the flux, the fluid also moves along the direction Z with a velocity Vz, there's a flux of momentum along x, along the Z direction, which is just proportional to the density of momentum along x times the velocity along the other direction. So it's very similar to this current here, except that now the density rho is the density of momentum in one of the direction you consider. Okay? Yes. It means that I work in the frame where the fluid is at rest. Here I consider that the flow is uniform, so all the fluid moves at the same velocity. Exactly. So and so I can define a frame where the fluid is at rest. And so by definition, in this frame, the velocity V prime is equal to 0. So now a priori, according to what I said, if you have a gradient of velocity, so you should have some momentum transfer. The thing that this effect, the transfer momentum due to some shear in the flow, is what we call viscosity. And here I'm going to consider a superfluid where viscosity is essentially equal to 0. So it means that the velocity, the momentum current of momentum will not depend on the gradients of the velocity field. It probably could depend on the gradient of the velocity field, and if I have time I will discuss that later. But since here I'm considering superfluid which has no viscosity, it means that it does not respond to a shear. It can sustain any finite shear without any dissipation, any force. And so I'm just going to stop my expansion here by saying so that even if there is a gradient of velocity, then the flux of momentum is not modified for that reason, because I have a superfluid. This is some kind of definition of a superfluid, something which do not respond to a shear.
So you consider that the superfluid fraction is 1? So
Yes, exactly.
Zero temperature.
Exactly. I'm in a superfluid state. I'm at 0 temperature. Yes.
Well, it's not just superfluid. It's
Yes.
zero
Yeah.
temperature.
I'm in a pure superfluid, or in the superfluid phase, as you say.
No, I mean, because if you just say you are in the superfluid phase, that means you are below TC.
I'm in a superfluid state, if you want. So
But then you have a normal fraction.
I agree with you.
So
Totally.
here you are at 0 temperature.
Yes. I'm in a pure superfluid. I don't have any dissipation, because you're correct. Even when I'm finite temperature, I have some dissipation due to the normal phase. Okay, so that's going to add some new terms that will depend on the gradient of the velocity field. So I will add some new term. plus something which is Cij KL dk VL at first order. So I can make an expansion in gradients in the sense that if I had terms which are second derivative of the velocity field with respect to velocity, so I'm considering here some long wavelength approximation in the sense that I will not excite microscopic degrees of freedom. So behind my formalism here, there is this assumption that all my perturbations have a long wavelength. Because if they have a short wavelength, the wavelength of my excitation can enter my mesoscopic volume that I define, where I can assume I have some thermal equilibrium. And so the local equilibrium approximation will not work anymore. And so that's why here when I have a derivative with respect to position like this, so it's going to scale like 1 over the characteristic wavelength of my excitation. When I consider a second derivative with respect to position, it's 1 over lambda square. Third derivative is going to be 1 over lambda cube, and so they're going to be smaller and smaller, again, because I am in the limit where lambda is large. And so all this to say that I can stop first at this first order, where I consider only the first derivative of the velocity field. And so the game would be to determine this quantity here. And so this quantity will define the different viscosity coefficients. Okay? And so now that we have this expression of the current of momentum, we can derive our full equation for the conservation of momentum, which is that d rho of Vi plus dj of P delta Ij plus rho Vi Vj is equal to n minus n times div. So I can write that the following way. So I have d rho Vi plus rho dt Vi plus di times P plus Vi times dj rho Vj plus rho Vj dj Vi is equal to minus n di sum V. So here I recognize the conservation of mass, so I can get rid of these terms here. And so if I divide by the density of particles, I finally end up with the equation that you probably derived with Misha-Baranov, which is the usual hydrodynamic equation for instance, a Bose-Einstein condensate, which is that m dt of Vi, so the derivative of the velocity along the direction I, plus Vj dj Vi is equal to minus div minus dip divided by n. So I have just one last step to really obtain the usual expression, which is to replace this expression here with the chemical potential. Again, using the Gibbs-Duhem equation, I remind you that tells us that VdP is equal to nd mu plus sdt. So again, I work at 0 temperature, so this is equal to 0. And so I have that dP over n is equal to d mu. So this term here is nothing but d mu. So finally my equation is m dt Vi plus Vj dj Vi is equal to minus div plus mu. so the chemical potential of the cloud. Any question? Good? Yes? Yes, totally. I neglected it when I suppressed this term here. So I said I'm in a superfluid at 0 temperature, so I don't have any viscosity. If I have time, I'm going to discuss the effect of viscosity, but it's here. I don't need to ask myself this kind of problem for the rest of the lecture. But I probably, yes, I should say at some point that the velocity field is the gradient of the phase of some order parameter, and so indeed this is irrotational. But for everything I'm going to say today, I don't need this assumption. Okay, so we're gonna try to look for some solutions of these equations, and the first simple solution we can, yeah, sorry. Not really, because by definition I removed all dissipation. But nevertheless, what you can find in these equations is the phonon modes. So you can find the dispersion of the phonons. And from the dispersion of the phonons, you know that you get the critical velocity if you lose Landau's argument. So my answer is yes and no. So, but you can see that if you take an object that you move, well, in some there is nevertheless this idea, because if you take an object and that you, so if my potential V is a moving potential, so V moves at constant velocity, you will see that it will create some kind of shock wave when the velocity is larger than the sound velocity, which is indeed in this included in this model. So it's probably not exactly the Landau criterion. It's some classical version of this criterion, but there is something that happens when you go faster than the speed of sound. It's some kind of supersonic bang when you move in the superfluid. Any other question? Okay, so the first obvious solution is to try to see what happens when the system is at rest. So in this case, the velocity field is equal to 0. And so the left-hand term of the equation disappears. And so what I see is that the right-hand term is equal to 0. And so V plus mu is just equal to a constant. And so I get that the chemical potential at point R is equal to mu 0 minus V of R. And so I recover the LdA. So as I announced at the beginning, this is indeed some generalization of the local density approximation. So now the other simple solution I would like to discuss is the situation that was discussed in Felix in his talk yesterday, which is the situation where I have a harmonic trap whose frequencies depend on time. So V of R and T is something which is like m over 2 sum over alpha of omega square alpha of T times x alpha square. So a harmonic potential whose frequencies depend on time. I should mention that in the spirit of the previous question, what you could look at is the solution for a uniform system which is weakly perturbed, and this way you can show that you can recover the usual hydrodynamic equations or propagation of sound and the sound velocity. But I will not discuss that today. And so what Felix said yesterday is that in the case of a isotropic potential, you can find some exact solution of the Schrödinger equation, of the many-body Schrödinger equation, in the form of scaling solutions. And what I'm going to show is that in the hydrodynamic hypothesis, and assuming that you have some polytropic equation of state, so mu is equal to A times the density to the gamma, then you still have some scaling solution to that problem. So why this problem is interesting? It's because it covers two or three of the limits of the BEC to BCS crossover. Because we know that for a Bose-Einstein condensate, the chemical potential is equal to G times N. So it corresponds to gamma is equal to 1. When I'm in the unitary limit, the chemical potential is equal to psi times the Fermi energy, so it's h bar squared divided by 2m times 6 pi square n to the 2/3. So gamma is equal to 2/3, sorry. And when I'm on the BCS limit, then mu is equal to EF, so h bar squared divided by 2m, 6 pi square n 2/3, and gamma is equal again to 2/3. Although I should say that the hydrodynamic limit is more difficult to satisfy in the BCS limit because the Cooper pairs are very fragile and so can be broken very easily. And so in this case, you leave the hydrodynamic approximation. But anyway, you see that all the three simple limits of the crossover are covered by this polytropic assumption. So to describe the scaling solution, we're going to assume that we're going to follow one particle. So here, this is exactly just like a hydrodynamic equation. So I'm going to use some classical pictures. So I'm going to assume that there are particles moving around in a fluid, just as they were very classical. There's nothing quantum anymore in what I'm going to be saying. So I imagine that a particle which is at position alpha naught, x alpha naught, at t equals 0, and at times t it moves at a position which is x alpha of t, which is lambda alpha of t times x alpha 0. So it means that its velocity in the direction alpha, v alpha at times t, is equal to lambda alpha dot times x alpha of 0. And so if I want to have the velocity field expressed at the local position I times t, I should replace x alpha of 0 by the position at times t. So it's going to be equal to lambda alpha dot divided by lambda alpha times x alpha. So this will be b alpha at point r. Okay. So if you rescale all the position, it means that the density will also be rescaled. So the density at point r and t will simply be the original density at position x alpha divided by lambda alpha. And if you want to normalize your density so that the atom number is constant, you need to divide by the product over all scaling coefficients. So this stands for x divided by lambda x, y divided by lambda y, z divided by lambda z. So it doesn't mean that this depends only on one coordinate. And so you check that this way, the atom number defined by the integral over whole space of the density is constant. Okay, and if you have this expression for the density, you get also a very simple expression for the chemical potential, because the chemical potential follows exactly the same scaling, except that this scaling coefficient here will be replaced by the scaling to the gamma because of that term here. So the chemical potential mu at point r and times t will be equal to mu 0 of x alpha divided by lambda alpha divided by the product over all coordinates of lambda j to the gamma. Okay, so now we have to put this and that in the hydrodynamic equations and see what we get. So so the derivative with respect to time of the velocity is pretty straightforward because I have the expression here of the velocity field, and so I see that the time is only on the scaling factor. So I have something which is lambda alpha dot dot divided lambda I dot dot divided by lambda I xi minus lambda I dot square divided by lambda I square xi. So I differentiate this with respect to time. Plus, so I have to calculate this quantity here that operate on the velocity field. So I see that the velocity field along I depends only on the coordinates I. So it means that there's only I equal j equal I that will contribute in this term here for that reason. And so when I differentiate vi with respect to xi, I get simply this scaling factor there. And so then I've multiplied by vj, and so I simply have, in this case, lambda I square, lambda I dot lambda I square times xi. So this is the initial part of the equation, which is here. Now I'm going to look at the the source part on the right hand side. So I have first the derivative of the potential, which is straightforward because the potential is written somewhere here. So I just have a force term, which is minus m omega I square of t times xi. And finally, I need to differentiate the chemical potential with respect to position. So I have the expression here. So that's going to give me something which is minus, so the scaling factor, pi over j of lambda j to the gamma times 1 over lambda I d of mu 0 divided by the xi estimated in xi over x alpha divided by lambda alpha. Okay. But now I know that mu 0 is a solution of the static problem. So d mu 0, the derivative of mu 0 with respect to position is equal to the potential. So I can actually replace this as dv divided by xi with the minus sign and estimated in x alpha divided by lambda alpha. So these terms here vanish, and so I'm left with m lambda I dot dot divided by lambda I xi is equal to m omega I square of t xi. So minus, so there's a minus and a minus, that makes me a plus, plus 1 over pi over j of lambda j to the gamma times m omega I square of 0 of xi divided by lambda I. So this is the force, initial force, estimated at point x alpha divided by lambda alpha. So all the m vanish, all the x vanish. There is a lambda I which is missing, which is here, which is this one. And so if I multiply by lambda I get lambda I dot dot is equal to minus omega I square t lambda I plus 1 over pi over j lambda j to the gamma times lambda I omega I of 0. So this is the equation I obtain. So these are the scaling equations that you need to satisfy to obey the hydrodynamic equations. So what Felix obtained yesterday is the case where all frequencies are the same, omega x equal omega y equal omega z, and gamma is equal to 2/3. It's because it's a chemical potential at mu equals 0 that enters here. Yes, yes. Sorry. Yes. This one? Yeah. Lambda prime over lambda. Here? Yes. I've got 3 equations. One for I equal x, I equal z. No, because it's only in the direction x, let's say. So the explicit expression will be Vx is equal to lambda x dot divided by lambda x times x. Vy is equal to lambda y dot divided by lambda y y. Vz is equal to lambda z dot divided by lambda z. Z. No, because I differentiate. Here I have 3 equations, one for direction x, one for direction y, one for direction z. And so I look at all 3 equations independently. And so when I differentiate with respect to time,
In fact, he come back to the x, y, z, which are independent variables with respect to t. Although he used the expansion lambda t to develop the space, then he come back in the real space.
there was another question on the left-hand side, no? Yes. Okay, did you answer Philip's, did you understand Philip's answer? No, so I came back to, so here the x alpha is the x alpha times t. So because now x alpha is an independent variable. So these are 2 points of view. So you can, when you have a fluid, you have 2 points of views. So either you take a particular fluid, which you know its position at times t equals 0, and you follow its trajectory. And so essentially here, the velocity will depend on time and your initial position. So the initial position will tell you where you were at times t equals 0, and so you know kinds of identify your particle. Or when you're doing field equations, what you do is that you look at a certain point at time t. So the point is located by x alpha, and you look at the velocity of the particle, which is at times t, at the point x alpha. And so this is what you usually do when you write these kind of equations, PDEs, when you consider that t and position are independent. And so that's what I'm doing here. So I start with the first point of view, I follow my trajectory, and then I switch to the other point of view by now looking at the position at a given time of my particle. It's a piece of fluid, yes. Particle of fluid, yes. No, it works essentially only for this, well, not only, but here it's because we have some polytropic equation of state and a harmonic trap.
How can you say that you
I would say it's more general because you can have all kinds of gammas here. But nevertheless, the scaling of the equation of state is still very simple. I wanted to add something. Yes, yes. What is nevertheless remarkable? So it's true that there are very specific instances where you can find these scaling solutions. But what I find also remarkable is that they're valid for any kind of magnitude of excitations. You don't have to make the assumption that the perturbation is very weak. You can nevertheless use these equations to describe the dynamics of the system. For instance, if you want to look at the time of flight, so you turn off the trap, and so the frequency omega I becomes equal to 0, then you can still use these equations. Okay? Any other question? So I said that we could use in any kind of situation, but I'm going to use them in a very simple situation where actually the perturbation is weak. And so I'm going to do exactly what Felix said before yesterday. So I'm going to consider a situation where we were at some initial frequency omega I0, excite the frequency to some value, and then come back to our initial value. And I'm going to assume that the modification of frequency here during this time is very small, so lambda, the scaling factor, is not very strongly modified. So I assume that lambda I is actually 1 plus epsilon I, where epsilon I is much smaller than 1. And so I'm just going to work in the during the time where omega, the frequencies, are back to their initial values. So I'm just going to look at the solution during that period of time. So I'm going to assume now that omega I of t is equal to omega I of 0 and equal to omega I square. And so if I linearize my equation, I get that lambda I dot dot will be equal, so epsilon I dot dot is equal to minus omega I square epsilon I. So this is the first term here. So there will be a minus gamma epsilon I that comes, so that will be a plus actually, that comes from this one here, plus gamma sum over j of epsilon j. And so here you see that you obtain a set of 3 equations for epsilon x, epsilon y, and epsilon z, which are coupled because this term couple all the different directions, thanks to which you can find the solutions, the eigenequation of your system. So I'm not going to solve that in the general case because time is running fast. Sorry. I'm just going to look at a situation where I have some very elongated trap along z, and so omega z will be assumed to be much smaller than omega x, which I take equal to omega y. The first gamma, this one, is this one here. No, sorry, it should mean gamma. Okay, you're right. Yes. 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 Yes, because we assumed that before t equals 0, the system was at rest. So lambda I was equal to 1 and lambda I dot was equal to 0. And so if this is equal to 0 and lambda I dot dot is equal to 0, then you have something which is constant, equal to 1. Okay, and so I'm just gonna look at symmetric mode. So epsilon x will be equal to epsilon y, and so epsilon z is something. And so essentially, so I'm gonna have two different modes. One which corresponds to a transverse breathing, where that we oscillate at a frequency which is comparable to omega x. So omega is the eigenfrequency of the mode, and so I will have a second mode whose frequency will gonna be similar to to omega z. And so, for instance, I'm just gonna consider this one, which is the easiest to look at. So my equation now becomes minus omega square epsilon x is equal to minus omega x square times, so there is 1 epsilon x here, so 2 epsilon x, plus 2 gamma epsilon x, there is one coming from epsilon x, the other one coming from epsilon y, plus gamma epsilon z, and minus omega square epsilon z is equal to minus omega z square times, so I will have 1 epsilon z, and 1 epsilon z here, so 2 plus gamma epsilon z plus 2 gamma epsilon x. So these are the general equations. So now I make the assumption that I'm looking at this mode here that corresponds to a transverse breathing. So essentially it corresponds to assuming that omega z is very small. And so I can forget about that term here if omega z is very small. So it means that epsilon z is equal to 0. So I can forget about epsilon z. And so I'm just left with this equation here that tells me that omega is equal to square root of 2 1 plus gamma omega x. So for instance, when gamma is equal to 1, you get that omega is equal to twice the transverse frequency, which is a well-known frequency for the breathing mode, transverse breathing mode of a Bose-Einstein condensate. If you want to study the other mode, when omega is equal to omega z, so what you must do is that to see that omega z is very small here, omega x is very large here, so you need to cancel that term, so that gives you a relationship between epsilon z and epsilon x that you insert in this equation here to obtain that relation there. And so if I look in my notes, I can give you the results somewhere. Blah, blah, blah. So it's omega z square root of 3 gamma plus 2 divided by gamma plus 1. No, small amplitude oscillations. Here I make the assumption that epsilon x, epsilon y, and epsilon z were small. Yes. Yes, because in the transverse motion, so it's a very fast oscillation, and so the axial degree of freedom do not have time to react, so they are frozen. While in the other case, you excite the axial degree of freedom, which is very slow, and so it drags with it the transverse degree of freedom, which reacts very fast, and so can follow the motion. So that's why you have this discrepancy between the two. So if you make the comparison with the experiments, you see actually what you obtain. So if you take gamma equal 1 for the BEC limit, you get the correct result. If you take gamma equal 2/3 at unitary limit, you get the correct result. We good? Okay, so now the problem that's what we've been doing here is very simple when we have some very simple equation of state. So this polytropic equation of state where essentially the chemical potential scales like a power law with the density. But now we know that the equation of state of a Fermi cloud in the crossover is much more complicated than that. And so in reality you should have to plug in the hydrodynamic equation, the correct equation of state, and so it's going to be quite difficult to solve. So I would like to show you another method that is kind of similar to variational methods, it's related to variational methods, and can allow you to get some estimate, and which are usually pretty accurate, of the eigenfrequencies of a cloud without having to solve these hydrodynamic equations. And so these methods are based on some rules. And hopefully I will have time in 30 minutes to cover everything I want on that topic. Okay, so let's consider a system which is described by many Hamiltonian H0, and let's assume that we want to know the eigenstates n and the energies, eigenenergy of the system. And I assume that n equal to 0 correspond to the ground state. So I'm going to excite the system with some excitation operator that I call f. And I would like to see the response of the system to this f. And so I introduce S of E, which is defined as the sum over n of n f0 squared delta of E minus En plus E0. So if you remember your Fermi-Golden rules, this quantity here is what appears in the excitation rate of your ground state if you excite it with an excitation which is something like f cosine of E divided by h bar times t. So this quantity here, up to a factor 2 pi divided by h bar, something like this, measure the response of your system to that kind of excitation. So essentially what it looks like, S of E, you see that F will excite the ground state to some state n, and so this will give you a result if the energy corresponds to the energy difference between En and E0. So typically it looks like this, with here En minus E0, where n corresponds to the mode which is the most excited by this operator f. And so I would like to know the moments of this distribution with respect to the energy. So I'm going to introduce m of k, which is the integral over all energies of e to the k times S of E. And so this is just the sum over n of En minus E0 to the k of n f0 square. And the miracle comes from the fact that these moments, or some of these moments, can be calculated exactly knowing only some very general macroscopic properties of the system, like its density profile, essentially. And this comes from some rules, relations, that can allow us to express exactly these quantities. And so I'm going to look at two cases, M1 and M minus 1. So let's look at M1 first. So M1 is the sum over n of En minus E0 of 0 Fn n f0 that I can write as the following: 1/2 of sum over n of, so 2 times 0 f e n n n f0 minus 0 e0 f n n f0 minus 0 f n n f e0 0. So why do I do that? Because here I have simply h naught times n. Here I have 0 times h0, and here I have h naught times 0. And so this way you see that I've introduced some closure relation that allows me to get rid of these n's, which are here, there, and there. And so in the end, I simply have something which is 1/2 of f twice f h naught f minus h naught f square minus f square h naught 0. And what is nice that this is actually a commutator. If I'm not wrong, this is f commutator with h naught f. And so in the end, you see that m1 is equal to 1/2 of f h naught f. So the expectation value being calculated on the ground state of the system. Okay, so how useful is that? Actually, very, because in a case where you have some excitation operator that operates only on the position, this has a very simple expression even for an interacting system. Indeed, so let's consider that the Hamiltonian h naught is the sum over all particles plus some interaction term that depends on positions. And let's consider an excitation which is, generally speaking, a sum over all particles of f of r alpha. So for instance, if the excitation might be a compression of your trap along some direction, so function f should be just, if you excite along z, just z square. You add a potential z square to your system. So now if you try to calculate the commutator of h naught with f, you see that this term will commute immediately with the interaction term. So this includes interaction, trapping potential, everything. So but this will go away. And so you're just left with 1/2m sum over alpha of p alpha square times f of r alpha. And so you can calculate very easily these commutators. And so this is 1/2m times the sum over alpha of p alpha minus I h bar times the gradient of f plus the conjugate minus A h bar gradient of f of p alpha. Oops. And so now you have to calculate a second time this commutator. Again, when you commute f alpha with p alpha, well, you just have to calculate this commutator. That's going to give you I h bar times, again, the gradient of f. So you're going to have h bar square divided by 2m times the sum over alpha times twice the gradient of f square. So factor of 2 vanish. And so in the end, what you get here is h bar squared divided by 2m times the sum over alpha of gradient of f square averaged. So this is there's 2 here. There's no 2 here. So if we take only for one particle, so it's n times h bar square divided by 2m times the mean value of gradient of f square for just one particle. So why is it really great, this equation? It's simply because here you see that we express everything in terms of a single particle observable. So as I told you before, if you take, for instance, f of r, which is just z square, so the gradient of f square is just z square again, with a factor of 2, but that doesn't matter here. And so you just need to know what is the square, the mean square of your mean square radius of your cloud to know this expression here. So this can be calculated just by knowing the density profile of your system. And since you can calculate this density profile using LDA, so this is a very simple quantity that you can calculate in practice. Okay. Finishing in 15 minutes is going to be challenging, but now let's go to m minus 1. Yes.
Because here you calculate the average of the cloud,
Yes.
but you didn't derive the actual shape of the mode.
I don't need the shape of the mode at this stage. Here I'm calculating something in the ground state. So the expectation values is taken in the ground state. The shape of the mode is given by the shape of f. So I'm gonna go discuss that at the end. So at the moment it's very abstract. You don't know where, probably don't know where we're going, but we're going somewhere. I promise. So let's look at m minus 1. So m minus 1 is the sum over n of n f 0 square divided by so it's going to be en minus e0. So actually the presence of this denominator here should remind you perturbation theory. And let's consider the situation where you perturb your Hamiltonian h naught into h naught plus lambda f, what I was saying before. For instance, you compress by some amount lambda, which is assumed to be small here, along the z direction. And so look at how the ground state is perturbed. According to first order perturbation theory, the new ground state, 0 of lambda, is given by 0 plus lambda some other all excited states of n f0 divided by e0 minus en plus subleading term. And so now let's try to calculate the mean value of f at lambda. So again, it's very similar to what Joseph discussed in his talk. What you're going to do is just keep the first order terms of this expression. So the first order is going to be, or the zeroth order is going to be 0 f0, so the mean value of f in the ground state. And then you're going to have the terms which are proportional to lambda, and you have two terms which are identical, which are just sum over n of 0 f n square divided by e0 minus en. And so here, up to the minus sign, you recognize minus 1, m minus 1. So this is f in the ground state minus 2 lambda m minus 1. So if you prefer, m minus 1 is can be interpreted as minus 1/2 times df divided by d lambda at lambda equal to 0. So again, if my f is some compression factor, what I look is the response. So f gonna be again the square radius of the cloud to a compression along z. And so again, this is all calculated in the ground state. So it means that I need to know how my static density profile changes when I change the frequency of the cloud. So the take-home message here that these two quantities, m1 and m-1, can be calculated directly from static properties of the cloud. Okay, so now it's time to conclude this very long formal parenthesis. Let's look at something which is m1 divided by m-1. So the ratio between these two quantities. So formally, this is the sum over n of En minus E0 of n f0 square divided by sum over n of 1 divided by En minus E0 of n f0 square. So this is the definition. Now let's call n equal 1 the lowest energy state which is excited by this f here. So the lowest energy state which has a non-zero matrix element between n and 0. So in this sum, it means that En minus E0 and f0 square will always be larger than E1 minus E0. And similarly, this one will be smaller than 1 over E1 minus E0, etc., etc. So I can write that M1 divided by M minus 1 is larger than E1 minus E0 square times the sum over n of n f0 square divided by sum over n of n f0 square. This simplifies, and so you see that this ratio m1 divided by m minus 1 gives me some upper bound for the energy difference between the ground state and the first state, which is excited by this operator f. So what I'm doing here is some kind of variational approach. You know, variational approach, you try to minimize some energy by finding the right wave function. Here what I'm going to do is to try to find the right operator that's going to bring me as close as possible to this bound here. And at the limit, if I'm lucky, I find an operator that excites only one mode. In this case, the sum is said to be saturated. So n, the sum over n, is restricted to only one element. And in this case, I can put just an equal sign and not a greater sign here. So if I'm lucky, or if I have some intuition, some good intuition, I can achieve m1, m minus 1, very close to E1 minus E0 square. So I probably won't have I won't have time to make the full derivation, but actually it's not so difficult to be lucky, especially in a harmonic trap. And so I let that as an exercise for you. But for instance, if you take for my function f z square, so you take an excitation along the z direction. So I shouldn't have erased that. So m1, as we said, will be n h bar squared divided by 2m times the mean value of the gradient of f. So gradient of f is going to be 2z, so it's going to be 4 times z squared, so it's going to be 2n divided by h bar squared divided by m z squared. So you can try to calculate that z squared using the local density approximation. M minus 1, as we said, will be minus 1 half d, so z squared divided by d lambda, but when I vary lambda, actually it's equivalent with varying the trapping frequency along z. So I have a m omega z squared divided by 2. So again, you calculate z square in the local density approximation and you vary z square, the radius square with respect to z square. And you make the ratio of these two values. And you will find that for a polytropic equation of state, we will recover exactly the hydrodynamic result. But you see here now that if you want to calculate these quantities, these frequencies for any equation of state, it's much easier. You don't have to solve some partial differential equation. You just have to plug your equation of state in the local density approximation, calculate z square, differentiate z square with respect to omega square, omega z square, and you get the result. You see, it's much faster. But it's probably not as rigorous because it requires a stage of luck at this step here. Okay? Not really here. I don't have any scaling assumption. I just need a luck assumption. And in 5 minutes, I would like to discuss very briefly a final experiment. Okay, I would like to discuss very briefly the Bragg spectroscopy method, which is a method that allows you to characterize these excitations. So it's very strongly related to what I've discussed right now about the sum rules, and actually there are some sum rules that allow you to interpret these data. But the idea of the Bragg spectroscopy method is very simple. You take two lasers like this with momentum Ka and frequency omega A, momentum wave vector Kb and omega B, and you interfere them on your cloud. So essentially what you create is some interference pattern, and since the frequencies at momentum Ka minus Kb, and since the frequencies of your two lasers are different, the interference pattern moves at a frequency or velocity, which is omega A minus omega B. And so for your atoms, they see some periodic potential that moves at some constant velocity. And so essentially, you have some excitation operator, which is Ika minus Kb times R, and exponential minus I omega A minus omega B times T. So this is the first point of view, and so you can plug this in the sum rule approach and get all kinds of interesting properties. The other approach, which is quite similar to what Philippe discussed in his last lecture, maybe before, is the fact that you have some two-photon process where you absorb one photon in one beam and emit a photon in the second beam. And so you transfer to the atoms a momentum which is Q equal Qa minus Qb, and a frequency or an energy, h bar omega, which is h bar omega A minus omega B. So in practice, it's very difficult to change the angles of these beams because you have to cross two beams at a micrometer scale on a cloud which is a micrometer broad, so it's pretty difficult to target. So once the beams are here, you're happy and you don't change them. But what you change is rather the frequency. And so what you what you tune is the frequency of your lasers, and you see whether you can transfer momentum and energy to the system. So the momentum is fixed, you vary the frequency, and so when you have one excitation which is resonant, so you had your atoms, your cloud which is in the ground state, and so plus one excitation, h bar omega, and so you want to have E0 plus some excitation of the, I don't know, how should I call that? Some many-body excitation, let's say. And so you want these two energies to be the same. So when you have one many-body excitation which is resonant with your excitation frequency, then you will have a response of the system. This is what you see. Here, this is a picture of the difference of the density profile of the cloud before and after the excitation. So here you have less atoms, here you have more atoms. It means that you have pushed the atoms, so you have transferred momentum when the frequency was right. And so to make a long story short, this is what you observed when you tune the strength of interactions from the BEC side to the BCS side. So here you see first you have these big peaks on this, let's say, the low frequency regime on the BEC side that corresponds to the phonons of your Bose-Einstein condensate. So essentially here what you excite are the usual Bogoliubov phonons of the Bose-Einstein condensate. So this way you can measure the sound velocity of your superfluid by looking at the position of the peak versus the momentum of the excitation. And here on the right-hand side of the graph, you see some broader structures that correspond actually to the Bogoliubov Bogoliubov-Dosian excitation that were discussed by Mira in his derivation of the BCS theory. So here you're looking at exactly this gamma k ek of something like this that you introduced in this in the BCS theory. And what is nice is that by this way, if you remember, on the BCS side, on the BCS theory, there was a gap in the excitation spectrum, and you can this way measure the gap. So for instance here, this is the result at the unitary limit, so you have a very broad and very big phonon peak, and here you have a very tiny BCS-like excitation. So here the excitation is mostly phonon-like, but you have nevertheless some weight on the Bogoliubov on the BCS excitations. And by looking at the well, if you maybe here the point where the energy at which this feature stops, you have an estimate of the value of the gap. And so that's the way they measured the gap. So these are the points here obtained by Bragg spectroscopy. By the way, BCS is here, and you have again all kinds of theories, Monte Carlo and others. I'm done. Unfortunately, I had only 3 lectures, so I could not cover everything I wanted. So there are lots of other experiments that I would have liked to discuss, but unfortunately, we had only 1 week. So I hope you enjoyed them, and if you ever pass to Paris, do not hesitate to come and visit us. Thank you. It's really that. So they measure the number of atoms which are expelled from the cloud. And so this is a measurement of this, that essentially the number of atoms is this red blob. Yes? It's more, it's not, because the V of k, you're probably referring to this V of k square. V of k square is really the momentum distribution in the ground state, so in the BCS state. So you take indeed one particle here and you excite it above. So in the spectrum of the gamma k states, which have this dispersion relation like that. but so these excitations here correspond to these broad features. Because here you have a gap, and so when you change the frequency, so when the frequency is below the gap, you don't have enough energy to to cross it, and so when you're above, you can excite all these states, and then you need to have a good overlap between the wave function, and so that's why it decays at large frequencies. But that's essentially the reason. So it's phonons. There's no gap with the phonons. You have a dispersion relation, which is just E equal h bar c times k, or yes. And so you give some momentum q to the atoms, you give them some energy, and so you want to be able, with this momentum energy, to create a phonon. It's because at 1k and it's essentially the main difference between this is that here you create only one quasi-particle, which is a phonon. So essentially, when you give a momentum q to the system, you give it to a phonon. When you give some energy h bar omega to the system, you give it to the phonon. So you have one possibility, which is having the right energy for the right momentum. Here you have a broad structure because you create pairs. So when you give a momentum h bar q, it's actually the momentum of the center of mass of the pairs. But you still have a degree of freedom for the relative momentum of the two. And so that's why you have some kind of continuum compared to this very narrow peak. True, but it's narrower than the continuum. Yes. Yes, exactly.